Hello everyone, so I'm going to be going over 1D briefly, which is about a store that sells Longjing and Dragonwell green tea bags, which is a pretty famous tea in China, and these tea bags come in packs of 4 and packs of 7. And we're defining a number n and saying that it's possible if we can attain n by some combination of 4 and 7. So for example, 4 is possible, of course, and 11 is possible because we can get a pack of 4 and a pack of 7, but then certain numbers like 3 and 5 are impossible, and of course, only regarding positive integers in this problem. So just to add some more context, a major difference between this problem and the previous problem is subtraction. Before we were dealing with liquids and we had one glass that could contain more liquid than another. So if we pour the liquid from that higher measuring glass to a lower measuring glass, we were able to retain the difference. So unlike those problems, we cannot subtract here. We have to make n using purely 4s and 7s. So as students explore this problem, they're going to find a lot of interesting patterns and initial observations. And one of the major things you're going to notice, of course, is that multiples of 4 work. You can get 4, 8, 12, and so on and so forth through some number of 4s. And similarly, multiples of 7 work. You can get 7, 14, and 21 through some numbers of 7. Now, some students who might want to be going beyond that will also notice that since 4 plus 7 is 11, multiples of 11 will work as well. You can get multiple pairs, or even more than pairs of 4 and 7s. So as I start to discover these different numbers that can work, they might begin shading them, or they might begin identifying them on this grid. So they might start to wonder, are there any other numbers, maybe some unconventional ones like 15 or 18 that work? They'll definitely notice that, for example, 4 plus 4 plus 7, like 15 will work, or 7 plus 7 plus 4, which equals 18 will work. But are there more of these types of numbers? Are there any patterns that we can notice with these numbers that aren't strictly like a multiple of 4 or 7 or 11? Well, actually there is, and as I start to observe, they might discover the following. So you can either, you have a lot of different types of numbers you can get that are possible, right? We already discussed a few of them on the previous slide. Another type of number that is possible to get is all multiples of 4 minus 1. And this comes from the fact that 7 is actually 1 less than a multiple of 4. So if you combine a certain amount of multiples of 4 with a multiple of 7, you are going to get a number that if you add 1 to it, you will get a multiple of 4. Right? And such numbers include 15 or 19 or 23, and the least such number is 7 actually. And you can also define multiples of 4 minus 2, right? And you can get this by getting, 2 multiples of 7 or some number of multiples of 7 and 1 multiple of 4. For example, 7 plus 7 works because it's just strictly 2 multiples of 7. And 18 works, right, because it's 14 plus 4. 14 is 2 multiples of 7, and 4 is just standalone. And this also comes from the fact that 7 is 1 less than a multiple of 4. And similarly, you can define 21. 21 is any multiples of 4, any multiples of 4, and subtract 3 from them. So students might initially start to find these types of numbers, and they might even in fact notice a pattern as they fill them out on the grid. Every fourth number, 15, 19, 20 through 27, etc. works, and they all share the common property that they're 1 less than a multiple of 4, and so on and so forth for all the blue, yellow, and pink numbers. Now, here that might start to be noticed, are there any numbers that we cannot get? Like, are there any unattainable numbers, as we defined before, impossible numbers? As they fill out the grid, they'll notice certain numbers like, 1, 2, 3, etc., you cannot get them. So they'll definitely be interested for that. So they can shade the numbers that are impossible in red. So they will quickly notice that, at least from 1 to 50, 17 is the greatest number that cannot be attained. And they now might wonder, is that true for numbers that are greater than 50? Like, will there be some number from 51 to 100, let's say, that also will be impossible, or is 17 the greatest? Well, as they try to discover more patterns and reason their way through this, they'll discover some really interesting things. So for any 4 consecutive numbers, let's just say 18, 19, 20, and 21, those are actually the first 4 consecutive numbers that are possible. You can simply add 4 to each of them, right? And you'll get 22, 23, 24, and 25, the next 4 consecutive numbers. So you're guaranteed, once you get a set of 4 consecutive numbers, that you will get a new set of 4 consecutive numbers. So that basically is one piece of reasoning that proves that any number greater than 18 is indeed attainable. Now, a very interesting fact is that 7 times 3 minus 5 times 4 is equal to 1. So whenever you have a number that contains 5 or more 4s, you can simply replace 5 of those 4s with 3 7s, and you'll get a number that is exactly 1 more than the original number. So that makes it really easy to see how you can get some of those higher numbers if the students don't initially notice the 4 consecutive number pattern. So through these observations, you'll eventually deduce that 17 is the greatest impossible number. Now, this problem is really interesting as you can generalize it to AB minus A minus B, where A and B are like the amount that the thing comes in. So here we have 4 and 7, so it'll be 4 times 7 minus 4 minus 7, which is 17, hence the 17. The proof for this is probably beyond the scope of this lesson, but it is a really interesting tidbit. And the 7 times 3 minus 5 times 4 linear combination is actually the basis of a proof of a very famous identity. So there's a lot of extension of this problem as well. But the main thing is the students start to, get their hands dirty. They start to uncover these new patterns, and they eventually are able to use some of these arguments to justify their reasoning. So yeah, thank you so much for listening.